Welcome back to AI.Code.Cast. You ready to dive into another coding challenge with me?
Always. What's on the menu for today's deep dive?
Today, it's word search 2. It takes the classic word search, the kind we all did as kids,
Yeah.
and cranks up the difficulty. Way up. Instead of searching for a few words, we're trying to find every word from a huge dictionary hidden in a grid of letters.
Whoa, okay, that sounds pretty intense.
It can be, but don't worry, we'll break it down step by step. First things first, though, let's make sure we're on the same page about the problem itself.
Sounds good to me. Lay it on me.
Okay, so picture this. We have a grid of letters, like a playing board, and we have a dictionary potentially massive, full of words. What's our goal here? What are we actually trying to find?
I'm guessing we need to locate all the words from the dictionary that are spelled out in the grid using adjacent letters, right?
You got it. You can move horizontally or vertically, but no diagonals, and you can't use the same letter cell twice for the same word.
So it's like tracing a path through the grid to spell out each word.
Exactly. And that's where things get tricky. If we just start randomly checking every possible path for every word, it'll take forever, especially with larger grids and dictionaries.
Yeah, a brute force approach like that would quickly become a computational nightmare.
Exactly. So we need a smarter approach, a more elegant solution.
Definitely. I'm already starting to think about how to tackle this strategically. What are some of the key questions we should be asking ourselves as we start to formulate a plan?
One thing to think about is how can we quickly determine if a given sequence of letters even has the potential to form a word from our dictionary. We don't want to waste time going down paths that lead nowhere.
Right, we need a way to avoid those dead ends early on, some kind of early warning system. So what kind of structure or technique could give us that kind of quick check?
It seems like we need a way to efficiently look up prefixes to see if the letters we're gathering have a chance of forming a valid word. Is there a specific data structure that's really good at that?
There is. Have you ever worked with a trie?
A trie, yeah. It rings a bell, but I think a quick refresher would be helpful.
Okay, so a trie is like a specialized tree. Imagine each node in the tree represents a letter, and each path from the top, the root, to a leaf node represents a word from our dictionary.
Okay, I'm starting to see the picture here. So if we were building a trie from our dictionary, each word would have its own little path, kind of like a branch, and each node along that branch would represent a letter of that word.
Exactly. And we'd add a special flag to the last letter node to indicate that we've reached the end of a complete word. This structure lets us very quickly check if a sequence of letters is a valid prefix.
Wow, this is starting to feel like a game changer. Instead of blindly exploring the grid, we could use this trie as a map. We can check at each step if the letters we have so far are even on the path to a valid word in the dictionary.
It's like having a GPS for our word search. And the best part is, if we hit a dead end in the trie, meaning the letters don't form a valid prefix, we can immediately backtrack and try a different direction.
Right, so we're not just wandering aimlessly. We're using the trie to guide our steps, making sure we're only exploring paths that have potential.
You got it. And that's where the concept of backtracking comes in. It's a way of systematically exploring all the possible paths in the grid, but using try to prune the search space as we go.
Okay, I'm definitely intrigued. Let's dive deeper into this backtracking idea. I imagine we start at a cell in the grid and then kind of branch out from there, right?
Exactly. We pick a cell, grab its letter, and see if it's in our trie. If it is, we can move to an adjacent cell, up, down, left, or right, and add that letter to our sequence.
Got it. Then we check the trie again. If it's still a valid prefix, we keep going. If it's not, we know we've hit a dead end, and we need to backtrack.
Yes, we backtrack, which means we go back to the last cell where we had multiple options and try a different path. And we just repeat this explore, check, backtrack process until we've considered all paths originating from that initial cell.
And then we move to a new starting cell and repeat the whole thing until we've covered the entire grid, right?
You got it. We systematically explore the grid, guided by our trie.
This is making a lot of sense. We're combining the power of the trie with a structured approach, backtracking, to efficiently navigate that grid.
That's the idea. Working smarter, not harder, to find all those hidden words.
I'm already starting to see how this approach transforms what seems like an overwhelming problem into something much more manageable. We've got our problem, we've tossed out brute force, and now we've got this amazing counter-explanation. Try to help us out.
A solid foundation, for sure. But now, let's talk about how we translate this into code. Imagine we're writing a function to solve this word search 2 problem. What would be some of the key steps?
Well, first thing that pops into my mind is that we need to build our trie. We need to take all the words from the dictionary and construct that specialized tree structure.
Exactly. How would you explain that try-building process? Think about explaining it to someone who's just learning about data structures.
Well, I'd probably say something like, imagine we're building a tree where each branch is a path to a word in the dictionary. Every time we add a new word, we add nodes for each letter, creating a path. And if a branch already exists for a letter, we just follow it.
Perfect. A nice, clear way to describe how we map the dictionary into this try structure, ready for those quick prefix lookups.
This is getting exciting. I can't wait to dig into how we actually use this, try to search the grid.
Me too. But we'll save that for the next part of our deep dive. Stay tuned.
All right, welcome back. Ready to put our try to work and find some words.
Absolutely. We've got our try all set up, ready to act as our guide. But where do we even begin with the grid search?
Right, think of it like exploring a maze. We can start at any cell in our grid, take that letter, and check if it's in our try.
Right. So if that first letter is in our try, we're off to a good start. We can then move to an adjacent cell, up, down, left, or right, and add that letter to our sequence. Exactly. Now we have two letters, and we go back to our try. Is this new sequence a valid prefix? Our try gives us a quick yes or no, telling us if we're on the right track.
It's like at each step, our try is saying, hey, this path could lead to a word. Or, nope, dead end, turn back.
I like that analogy, but what happens when we hit that dead end? What do we do?
That's where backtracking comes in, right?
Yeah,
If the current sequence isn't a valid prefix, we got to go back, retrace our steps, and try a different direction from the previous cell.
exactly. We backtrack to the last point where we had multiple choices and explore a different branch. And we keep repeating this process, exploring, checking with our try, and backtracking when needed until we've considered all the paths that start from that initial cell.
Okay, I'm following. So once we've exhausted all the paths from that starting cell, we move to a new cell and repeat the process. Right. Keep going until we've covered the entire grid.
You got it. Now imagine as we're exploring, we stumble upon a path that leads us to a leaf node in our try, meaning we found a complete word.
We celebrate. Well, maybe mentally. But then what? We add that word to our list of found words. Do we stop exploring from that point?
Not necessarily. Remember, a word can appear multiple times in the grid, starting from different locations, so we have to keep exploring. But there's a little optimization we can do here.
Ooh, I love optimizations. Tell me more.
As we find words, we can mark the corresponding path in our try as visited. That way, if we come across the same sequence of letters again, we know we've already found that word. It saves us from adding duplicates to our results.
Ah, clever. It's like we're leaving breadcrumbs in the dire leather. Try to avoid revisiting the same path. Any other neat tricks or things we should watch out for?
Definitely. One common pitfall is forgetting to unvisit cells in the grid when we backtrack. A cell might be part of multiple words, so we need to reset its visited status when we back up.
Right, we don't want to accidentally block off a valid path just because we used that cell in a previous word. It's all about keeping those options open.
Exactly. We need to maintain that flexibility in our exploration. And another point, even though we're trying to avoid duplicates in our final list, we might encounter the same word multiple times in the grid, just starting from different cells. We need to handle that, making sure we only add each unique word to our results once.
So it's not just finding the words, but finding them efficiently and making sure our final result list is accurate and clean. It's like meticulous detective work, gathering clues, following leads, but also organizing our evidence carefully.
Great analogy. So imagine we've meticulously explored every cell in our grid, we've diligently checked our try at every step, and we've backtracked when needed. We have our list of words. How do we make sure our solution is working correctly?
That's where testing comes in, right? We need to create test cases, maybe some with small grids and dictionaries, some with larger ones, to see if our algorithm produces the expected results.
Exactly. Throw in some edge cases too, like what happens if the grid is empty or if the dictionary is empty. We need to make sure our algorithm handles those situations gracefully.
This is really coming together. We've gone from this somewhat abstract problem to a concrete understanding of the solution, and now we're even thinking about how to test our code.
It's like we've created a blueprint for our word-finding machine. Now we just need to start putting the pieces together and make sure everything runs smoothly.
I love how this is unfolding. We have our try, we know how to use backtracking, and we're considering potential pitfalls and how to test. What's next?
Well, we've talked about the algorithm conceptually. Let's get more specific about how to actually express it in code. Imagine we're writing that function to solve this problem. What would we call it?
How about find words? It takes our grid and dictionary as input
Right.
and returns a list of the words we found.
Perfect. A nice descriptive name. Now, what would be our first step inside this function?
Well, we need to build our try. We could have a separate function called maybe build try that takes the dictionary and returns the constructed try.
Right. So inside our find words function, we call build try to get our try all set up. What next?
Time to start exploring the grid. We can use nested loops to iterate over each cell.
Good. So for each cell in the grid, what do we do?
We check if the letter at that cell is in our try. If it is, we can start exploring paths from that cell.
Okay, and how would we actually go about exploring those paths?
That's where backtracking comes in. We could create another function, maybe explore, that takes the cell coordinates, the current word we're building, and the try as input.
Excellent. This explore function is the core of our backtracking logic. It would call itself recursively to explore adjacent cells, building the word character by character, and using the try as its guide.
This is starting to feel like real code now, breaking down the complexity into smaller, manageable functions, each with a specific purpose.
Exactly. And within our explore function, we need to take care of all those little details we talked about earlier, marking cells as visited, unvisiting them as we backtrack, and avoiding those duplicate word additions to our result list.
I'm seeing how all the pieces fit together. Find words orchestrates the process, build try creates our guide, and explore does the heavy lifting of searching. And we're being careful to handle those tricky situations and optimize where we can.
Fantastic. We've gone from a high-level overview to a more concrete grasp of the code's structure. What else should we keep in mind?
We've really fleshed out the solution, haven't we? We talked about using a trudge, tried to guide our search, backtracking to explore the grid, and we've even touched on optimizations and potential pitfalls. But now I'm curious, how do we know how efficient our algorithm actually is?
That's where big O notation comes in. It helps us analyze how the performance of our algorithm scales as the input size grows, both in terms of time and space.
Right, so if we had a much larger grid or a dictionary bursting with words, how much longer would our algorithm take? Let's start with time complexity. What factors influence how long our algorithm runs?
Okay, well, we have two main phases, building the try and searching the grid. For building the try, the time it takes is basically proportional to the total number of letters in all the words in our dictionary.
Okay, so more words or longer words mean more nodes to create in our try and therefore more time. What about the grid search? That seems a bit more intricate.
It is. In the worst case scenario, imagine we have to explore every single path in the grid up to the maximum length of a word in our dictionary. And we have 4 directions to move from each cell, so things could really branch out quickly.
Yikes, I can see how that could get out of hand. So if we have a 10 by 10 grid and our longest word is 8 letters long, that's a lot of potential paths.
Exactly. But remember, our try is our secret weapon. It's constantly pruning our search space, preventing us from going down paths that won't lead to valid words.
Right. It's like the try is constantly saying, nope, this path is a dead end, turn back. It saves us a ton of time by avoiding unnecessary exploration.
Exactly. So the actual performance is often much better than the theoretical worst-case time complexity, all thanks to our try guiding the way.
That's reassuring. So what about space complexity? How much memory does our algorithm use?
Well, the main thing that takes up space is our try. The more words and the longer the words in our dictionary, the bigger our try gets.
So it's similar to time complexity in that sense. The size of the dictionary has a direct impact. We also need a bit of extra space for our results list and keeping track of visited cells, but that's probably small compared to the try.
You're absolutely right. The try tends to be the dominant factor when it comes to space complexity.
This whole discussion about complexity has been really helpful. Now I'm wondering, are there other areas where this try-based approach is used?
Oh, definitely. Tries are incredibly versatile. One classic example is autocomplete suggestions in search engines. As you type, the search engine uses a mitral to cheer. Try to suggest words that start with the letters you've entered.
That makes perfect sense. The try is like a guide, helping the search engine narrow down the possibilities as we type, just like it's guiding us through our word search grid.
Exactly. And think about spell checkers. They often use tries to efficiently check if a word is in the dictionary. It's all about those quick prefix lookups.
So tries are helping us avoid those embarrassing typos. Any other cool examples?
They're even used in networking, like in IP routing, where routers use tries to quickly match IP addresses to network paths. It's amazing how this one data structure has so many applications.
Wow. I'm really impressed by how versatile tries are. Definitely a powerful tool to have in our coding toolkit. Well, this has been a fantastic deep dive into word search too. We've covered the problem, come up with a solution using tries and backtracking, and we even explored the efficiency of our algorithm and saw how it's used in the real world.
It's been a great journey. I hope everyone listening feels ready to tackle word search too and other challenges that involve efficient prefix matching.
Me too. And maybe they'll start noticing tries popping up in unexpected places in their daily lives. Thanks for joining us on this coding adventure. Until next time, happy coding.